Okay, so what I want to look at is, derivatives of, exponential functions, or I guess functions base e. So we're going to look at natural log, and we're going to look at e to the x. Okay, and so what I would like to do is have you, go into your calculator and actually graph y equals ln x. And you could graph y equals ln x, and you could look at what the values are, like natural log of 1, which we should know is 0, and then type in the decimal approximations of the others. So I know that one's 1. It's whatever ln of 2 is, whatever that decimal is, whatever natural log of 3 is, whatever natural log of 4 is, whatever natural log of 5, natural log of 6. But then more importantly, let's use our calculator to find the derivative. And this is something that we have not done yet on the calculator. So I'm going to see if I can pull this up. I'm going to try to pull this up maybe. Let's see. Let's see if I can do this. Just close my laptop from laptop view to tablet view. Okay, so I can go perfect. So I'm going to go to my graphing calculator, which is right here, or at least an online version of it. Okay, so I went ahead and typed in y equals the natural log of x, and I went to my graph, right? And so just so you know, you can calculate values. So go to second, calculate, and let's say you wanted to know what is the value at 2, right? If you want to know what the natural log of 2 is, right, you just put in 2, hit enter, and it'll tell you, oh, 0.69314. Awesome. Okay. So you could get those decimals. That's fine, right? You can go or you could even just go to your table, right? So I think an underused feature is your table values. Now I still have my window set to pretty small because I was looking at the limit values, but you just go to your table setup, and let's say you just start at 1, and let's say you change by just an integer at a time. And so that way, if you wanted to see what were those values, there's natural log of 2, 3, 4, 5, 6. Okay. Now, so then let's also find the derivative. So let's see how the calculator can do that. So here's our graph. So back to second, calculate. Look at that option right there, number 6, dy dx. It's gonna take the derivative at a particular point. Well, now what I don't really like about our calculator, and I feel like I've said one of my life goals is to create a better calculator, and I don't like that it doesn't show what you just selected. It doesn't say dy dx until you hit 2, and then so x equals 2. Oops, not 22. I'm sorry. X equals 2, and then hit enter. And there's our derivative value. Dy dx is 0.500000. Okay. So then go back to your table here, and you could write I'm going to try to write. There it is. 0.00. Oh, sorry. 0.5, which a whole bunch of zeros, which if you're doing 3 significant figures, to be 0.5. Okay. So then let's try natural log of 3. So then the derivative, again, you could go second, calculate dy dx, and then let's pick at x equals 3. 0.333, 0.3, almost 0.3 repeating. It's probably pretty close to 0.3 repeating, simply because our calculator could just be doing some kind of algorithm or something like that, like a rounding error, or some kind of by the time it gets out to that many decimals. Okay, so let's see what the next one is. Let's go second, calculate a specific derivative value at 4. 0.25000. Okay, so now I'm starting to see a pattern. I'm hoping you see that too, right? And so just in case you don't, and to complete this table, go to natural log of 5. But if you see the pattern, you might be able to already guess what this is. Okay, so find the derivative value at 5 and exactly 0.2. Interesting that there's no other decimals, right? It's just 0.2. So go back and fill that in, right? 0.2. And so then the natural log of 6 value. Okay, so the derivative of natural log when evaluated at 6. So we'll do one more time. Second, calculate and we pick 6, and second, calculate the derivative value of 6. Okay, 0.16666 repeating. Okay, so like I said, I hope that you're able to kind of deduce based just numerically on what we found. If you're feeling that, yep, there we go. 0.16 repeating. That really 0.5 is the same thing as 1/2. 0.3 repeating is the same thing as 1/3. 0.250 is the same thing as 1/4. 0.2 is the same thing as 1/5, and this would be the same thing as 1/6. In other words, the derivative of ln x is 1 over x. So that's pretty cool. Okay, so the derivative of the natural log function is 1 over x. Now, that's an easy derivative to remember. I mean, this is one thing to remember, but now we're going to combine it with chain rule or product rule or quotient rule, right? Of course, it's AP Calc. So now the nice thing is that it doesn't really matter what your it doesn't really matter like what your natural log is. So inside, like if you don't, okay, natural log of something, it does not matter. The natural log's derivative, if I go back here, is 1 over what that thing is. So the derivative would be 1 over that thing. So what was that thing? That thing was 6x. So then I put a 6x down here. Oops, I will try to put a 6x down there. Pen. Okay, wow. One more time. Pen, yes please. 6. Okay. Oh my gosh. Case of the Mondays for Mr. Brown, because I have it set to such a thick pen. There we go. Okay. 1 over 6x. But then chain rule, what's the derivative of 6x? It's 6. So those cancel, and you actually just get 1 over x. Now, that's our answer, which is kind of interesting that the derivative of ln of x is the same as the derivative of ln of 6x, right? Even though there's like a 6 there. But think about this for just 1 minute. There are log properties like natural log of AB is equal to natural log of A plus the natural log of B, right? So if you applied a log property first and said, okay, so now let's do natural log of 6x is the same thing as natural log of 6 plus the natural log of x, and then take the derivative. Well, the natural log of 6's derivative is 0 because it's a constant, albeit a transcendental number. And then the derivative ln of x is 1 over x. So again, it doesn't matter if you algebra first or calculus first, you get the same answer. Okay, so you could always take log properties if you want, if you think it helps simplify things. You don't have to. Just remember chain rule. So derivative of ln, again, it doesn't really matter what that's what's in there. The derivative is always 1 over. Oh my gosh, so frustrating. I'm gonna learn my lesson here. 1 over that value. So the derivative would be 1 over whatever that is, which we said was x squared. Okay. Why is it defaulting to that? That's so funny because I can never get to default to anything I want. Okay, and then chain rule, derivative of x squared, which is 2x. Okay, this simplifies to 2 over x. And again, using a log rule, if you want to use the log rule first, one of the rules is that natural log of x squared, that exponent of 2 could come in front. So it's twice natural log of x. So its derivative would be 2 over x, right? Because the derivative of ln x is 1 over x. So again, same thing. Now, here, just be really cautious. You can't really simplify. I mean, you can't pull a subtraction or a difference out of the log. If it were a difference of 2 separate logs, you could put them together in a quotient, right? So log of a minus log of b is equal to log of a over b. That's a rule, but there's nothing here about subtraction. So I'm going to do 1 over x to the 4th minus 2x squared times the chain rule. What's the derivative of the inner function? 4x cubed minus 4x. Okay, and then that could go in the numerator. So 4x cubed minus 4x, all divided by x to the 4th minus 2x squared. Now, you might notice that you could factor out, an x value here. So then if I do that, that becomes 4x squared minus 4, over x cubed minus 2x. So you still want to simplify it as much as possible. Okay, next one. How cool, the natural log of sine of x. So, oops, too far. Getting ahead of myself here. One more. There it is. Sorry. I feel like this has been such a weird video, like just little things that just aren't running as smoothly as I like them. That's okay. Makes it interesting. The derivative of ln is 1 over whatever that thing is. And like initially, again, I think I mentioned this in the chain rule video, don't take too many derivatives at once. You can do one derivative at a time. So the derivative of ln is the reciprocal function, 1 over sine. Now do the derivative of sine, which is cosine of x, and that conveniently and neatly simplifies to cotangent of x, right? Cosine over sine, okay? Similar things can happen here. Natural logs of derivative, again, the derivative is 1 over that thing. And then what's the derivative of cosine? Negative sine. So then this can simplify to negative tangent of x. Which is kind of interesting, I think, in a way that like the natural log function somehow kicks you back to that function of a trig function. It's kind of interesting to me. Okay, I think there's 2 more examples here. One dealing with a product rule, and one dealing with a quotient. So again, product rule, take turns, right? The polite product rule. So the derivative of x cubed is 3x squared. You leave the natural log alone, plus x cubed and the derivative of ln, which is 1 over x. Now, this one didn't have any chain rule on the inside, so we're okay. So then we could just leave it as 3x squared times natural log of x. And I might make, again, that dot there just to emphasize that's a separation by a product, plus x squared. Now, I noticed there is a GCF of x squared. I could have factored out. I didn't. Okay. And then I think, this will be the last example on this video. Quotient rule, just for fun, right? So low, which is x, d high, 1 over x, minus high, natural log of x, d low, 1, all over low, x squared, which is equal to, well, this just cancels to 1 minus ln x over x. Okay, excellent. So, again, sorry for the little bit of awkward and cumbersome moments in this video. But again, the whole point I wanted you to see at the beginning is, well, 1, to kind of make you aware of a feature on our graphing calculator, but then also 2, to show numerically that we can prove the derivatives of natural log is equal to 1 over x, or 1 over that function. Okay.